We've so far learned that flexibility is crucial for successfully integrating wind and solar energy into electricity grids. We've also learned that electricity systems already have a lot of flexibility built into them to deal with unexpected changes in demand and supply. We know that increasing the share of renewables like wind and solar increases flexibility requirements, and in this topic we're going to drill down into how the additional flexibility can be provided.
It should have become clear by this point that all electricity systems, regardless of solar and wind penetration, are designed with an inherent degree of flexibility so as to respond to the variability and uncertainty associated with changes in demand, as well as planned and unplanned outages of power plants and transmission components. Introducing significant levels of solar and wind energy increases variability and uncertainty in the electricity system, and therefore increases the need for system flexibility. Fortunately, numerous sources of flexibility are available to electricity system operators and planners. This chart, which we refer to as the flexibility supply curve, identifies many flexible measures and organises them roughly according to their relative costs. Please note, however, that the actual costs and relative ordering of these measures is system dependent and may change over time as technologies evolve. For most electricity systems, the least cost sources of power system flexibility fall into the category of improved electricity system operations. Examples of operational measures include implementing solar and wind power forecasting, which reduces the uncertainty associated with these resources. Another option is to increase the speed of electricity system operations, for example by moving from hourly dispatch to 15 or 30-minute dispatch, which allows the operator to make cost-effective adjustments to changes in solar and wind output. A final example is improving coordination with neighbouring electricity systems, which may be able to provide additional resources to balance supply and demand and to provide reserves. Operational measures tend to be lower cost than adding new capital infrastructure, such as new transmission, energy storage, or flexible conventional generators. However, successful implementation of these measures may require significant changes to institutional mechanisms, regulations, and policies.
Managing load is another relatively low-cost form of flexibility. For example, demand response programs can incentivize electricity users, be they households, businesses, or large industrial manufacturing facilities, to turn down their demand when wind and solar generation is low. This can be done in a number of ways, for example through time of use tariffs, or through direct arrangements between electricity providers and large electricity users. It can also be done through more dynamic mechanisms, for example smart meters, which can indicate when electricity supply is scarce and electricity expensive. It can be done through smart electricity networks, whereby electricity using devices can talk to the system and switch themselves on and off in response to supply and demand imbalances.
A third source of flexibility is the generation fleet. In some cases, the system operator can access flexibility simply by operating existing conventional plants differently, but within their physical capabilities. For example, changing their output or ramping them to balance net load fluctuations, operating them for longer periods at their minimum stable output levels, or starting and stopping them more frequently. A potentially more expensive option is to retrofit existing conventional power plants to enhance their flexibility. Beyond conventional generators, modern solar and wind power plants themselves can provide flexibility when they are equipped with advanced controls that allow them to change their output in response to commands from the system operator. Extracting flexibility from renewable energy generators might require changes to interconnection requirements, contracts, and operating and market rules. Flexibility can also be provided through enhancements to transmission and interconnections. These can include upgrades to existing transmission capacity or new transmission infrastructure. Grid expansion over extremely large areas is viable by the use of very low power loss, high voltage direct current lines, or HVDCs. In general, larger and more interconnected transmission systems are more flexible than smaller and less interconnected systems, due to their ability to access more numerous and diverse balancing resources. For instance, if two neighbouring power systems experience different weather and/or demand patterns, for example if they're in very different time zones, then strong interconnections and coordination between the two systems can help to ensure surplus renewable energy generation in one system can meet demand in the other. Finally, we are increasingly seeing the use of electricity storage technologies, be they pumped hydro plants, batteries or other technologies, to help store electricity at times of surplus and release it when required. Many storage technologies are still considered emerging and are relatively expensive. However, battery storage costs in particular have been declining very rapidly in recent years.
Key to the use of any of these flexibility measures is planning. This refers to the initial data gathering through to the simulation of the operation of these renewables in electricity systems. It's important to consider the unique characteristics of these renewables in terms of their low operating costs, the variability and uncertainty of their outputs, and their locational specificity when planning the cost-effective flexibility measures to deploy in the near term, the medium term, and the long term. The different flexibility measures discussed in this video, ranging from the initial planning through system operations, demand response, flexible generation, and enhanced interconnection and transmission expansion, are discussed in further detail in the additional material that accompanies the video. Also in this additional material are a number of real-world examples of how different countries have successfully and cost-effectively integrated variable renewables into their electricity systems.